So our goal to this morning, before we start looking some more at the problems that some of you are saying I'm behind on finishing, I'm not adding any other lengthy assignment to this today, and you will have a good amount of time to work, but you do need to make sure you guys are working and really looking at it. I haven't been here, so I can't say you have or haven't been. I'm just saying you need to make sure that you are using your class time as much as you can, because if a lot of us are getting done with them, and some of us are not, that probably means that some of you need to work a little bit harder, work a little bit smarter while you're in here. If you still need more time, then you're always welcome to take a book home with me and just let me know what you're taking, so that way you can get it done. But you are going to be looking at turning these problems in, remember, next week. So you're going to want to have that kind of in the back burner. I know you guys have a lot going on between now and then, so just while you are in here, and this is the time you can focus on it, try to do that for me. We're going to do 8 problems this morning that are getting added to the problems that you're supposed to have done, but I'm not adding any more after that. So we're going to try a couple, and you're going to try a couple, and then I'll let you continue working on the problems that you've been assigned for. So the ones that we're picking right now are piecewise functions, they're called. And you see one of them in front of you. So think back. You should have at some point seen something that looks like this. Even if you haven't, when you hear the word piecewise, think about what that word might mean. You look at the problem in front of us that we're supposed to graph. Anyone describe for me what they think we're doing? Okay. There's one equation, and he says there are 2. Can someone tell me what the 2 are that he sees? Okay. So you can see the 2 equations, and you should have a pretty good idea of what those 2 equations look like. What type of equations are they? Start with the 3 minus x. It's what? It's a linear equation. So that one looks like a line, and 2x is also linear. They're both linear, but they're different functions. They have different slopes, different y-intercepts. And basically, yeah, like Riley said, a piecewise just means you're splitting it up into pieces. So if I were to tell you to graph 3 minus x, I would bet money on the fact that everybody in this room could make that happen. If I were to tell you to graph 2x, everybody in this room could make that happen. But I did, after each of those pieces, give you a requirement. Yeah, there's a rule for what x actually is in the graph there. So basically, all a piecewise function is it's a function where you graph multiple pieces, meaning both of these together make up the function. And the first part right here is only going to get graphed wherever x is less than or equal to 1. So think about splitting your graph window. Here's x is equal to 1 right here. I'm saying everywhere that x is less than that, which would be on which side? The left side. And it includes 1 because it's got the or equal to, we're going to graph 3 minus x. So if you were to start graphing 3 minus x, what would you do first? Start at there. Where would you put your first point on your graph? If I just told you graph 3 minus x.
Start on the 3.
On the 3, okay. On the y, okay. So here's its y-intercept. That's a point on it. And then what would you do? Down 1 and over 1. So it has a slope of down 1 over 1. Okay, so it would look something like this. And I would graph a line through it. But what this is saying is that I only want you to graph this line everywhere that x is less than or equal to 1. So if you think about this red arrow right here being the cutoff to the graph, I'm wanting you to graph this line only over there. That's what that top line means. And notice it does say less than or equal to 1, so it does include that spot there at the end. So to make a piecewise function, you graph it in pieces. I'll go to the second piece. Second piece says 2x. What would you do first? Okay. My y-intercept is 0. And then what would I do? Okay. So here's a point, and here's a point, and here would be a point, and here would be a point. And I would draw a line through it. But the function says that part or that piece only gets graphed where 1 is less than x, or in other words, x is greater than 1. So I'm going to go to the x equals 1 spot on that line, which is actually where this one is as well. And I'm going to only graph the parts of the function that are to the right. So what you end up seeing is a different looking picture than you would normally see, but it's made up of 2 lines that are both only graphed on a certain part of the graph. That's all a piecewise function is. So again, we don't really do them much in Algebra 2, even though that's where they really belong. We don't really have a lot of time for them. The reason we're going to look at them now is because when we get into calculus and we start studying change and rates of change, that's the whole idea behind calculus, is how things actually change. When we get there, we're going to have to look at situations that actually go for certain amounts of time and then they completely change. And so you'll look at x being like your time axis, and so it happens one way for a certain length of time and then it stops and something happens differently. Okay, so let's look at a second one and let's see if we can break it down. You're going to have to be really, really good with your functions. So what you're going to see is that they don't get any harder than what we just did, but you knowing your functions and knowing how they get translated is going to be the hard part. So you have to know when you see an equation in there, when like Riley looked at it and said they're both linear, you have to be able to know that they're both linear. You have to be able to know what they look like, what their shape is, and how they get translated so that you can graph them quickly. That's the hardest part of this. So I gave you 2 pieces to this one. What does the graph y equals or f of x equals 1 look like? Is it vertical or horizontal? Yep. This is a horizontal line. It's supposed to cross through 1. And this says everywhere x is less than 0. So here's my x equals 0 line right on that axis. I'm going to only graph that horizontal line to the left. Now the first one started out x is less than 0. So technically right here, it doesn't actually cross this axis. For now, because this is the first one I'm doing, I put an open circle there, which indicates to you what?
A hole.
Okay, yeah, it's like a hole. It doesn't actually exist there. It runs into it, though. On the last one, it was solid at first, and then when I started the next one, even though the next one didn't have that or equal to piece, it was the same point. So it had already been filled in. This point might get filled in a second. I don't know. I'm going to look at the next piece, square root of x. What does that graph look like? It's a different sort of curve. What is it? What did you say? Yeah, it does swoop. Which way does it swoop? Yeah, that is a good question. Yep, it's like this. That's what Hannah's drawn in the air. If you weren't sure, you have a couple options at this point. You could graph one on your graphing calculator. Jules just pulled hers out and she looked at it. When you graph, did you actually do square root of x? Just that plain thing? Where does it cross the x or the y-axis? Starts at 0, 0, so it goes like this?
Yeah.
And it looks something like this. Okay. So your job would be to know the basic shape at least. That would be our hope at this point. If not, you could graph it on a calculator. You could also graph it with some points. So if I wanted to know actually in terms of me putting it on this graph, we can see it starts here. And I'm going to leave this closed because this does say or equal to 0. But in terms of me putting it on a graph, at least in getting a couple points correct, I need to know where it crosses when x is 1, for example, and x is 2, and x is 3. You can do that the same way you would have done back in the old days if this was just the only equation you're graphing. If I told you I needed you to graph y equals square root of x, and I needed you to figure out a point when x was 1, so I knew how high to actually put it, what would the answer be? Yeah, so 1. What about 2? It is 1.4. So I could think through a quick little table in my head, or I could graph it and I could actually see, but that means there's a point right here, and there's a point at 1.4. At 3, square root of 3 is about 1.7. At 4, that's where I would hit 2. So I just get enough points on there so I get a pretty good feel for what it looks like, and I draw it. That right over there is the actual graph of the piecewise function. So again, the hardest part's going to be that there's multiple pieces, so no longer do you go, oh shoot, I don't know that one. Sometimes you don't know either of the piece or what they look like, and so you have to investigate a little bit.
Is that an arrow at the end of that?
Yes. Yeah, this was just an arrow saying that this pattern would continue. And really then, I would have an arrow here as well, saying that that continues, because it does say everything as x is less than 0. It's a weird looking graph. Okay. So here's a piecewise that's defined in 3 different pieces. Our job is to graph all 3 pieces only on the parts of the x-axis that it tells us to. So the first part is everywhere x is less than 1. So that's going to be a cutoff for us. And then the next piece is going to go between 1 and 3. And then the next piece is going to go bigger than 3. So now we've got 2 stopping points to think about on our graph. So you just do them in pieces. We have to know what 4 minus x squared looks like. Okay, it's a parabola. We're going to have to graph it. What's the parabola look like? What's that? It's facing downwards. It starts at 4. Good. So your translations are going to be super helpful to you. It starts at 4. It opens down. We're supposed to graph it to this point right here. So what I would do is I would think about where would I hit on this x equals 1 line. If 1 was plugged into the equation, what would the answer be?
3.
So that means it's going to hit here. And that we know that it's a parabola that opens down. Brenna says this is the top of it, which means it's a mirror image. It has to go like this. But I'm going to stop there. And for now, I'm going to make that an open circle because it doesn't actually include 1. But that's the left-hand piece. And then I'm going to look at the next piece. And I did all that work, but it was just for 1 out of 3 pieces of it. So you go to the next function in it. 3 over 2 is what that's supposed to say. It looks hard to read from over here. It looked fine when I was on top of it. What's 3 over 2x plus 3 over 2 look like? Okay. So in terms of my graph, it starts here, but I'm not going to end up needing that point in a second. And this is the hard part about drawing them. Sometimes you start sketching on your picture because we always rely on that y-intercept to get us a starting point and then to start counting. But that part's not going to actually get graphed. I just need to see it. Then I'm going to go up 3 and over 2, he said. So if this is at 1.5, up 3 would get me up to 4.5. And then I'm supposed to go over 2. So I'm supposed to draw a line straight through those points. But I'm only going to actually draw this from 1 to 3. So if you connect from here to here, the nice part is you do actually go through that point. I don't actually want this piece of it. Notice this dot happened to get colored in because it's part of this graph, and it would continue going like that from 1 to 3. So I'm going to cut it off when I get to 3 with a closed circle. And then the last part is x plus 3. What would you do if you were told to graph that? Okay. So I'm going to do this in a different color just so I don't get confused, because I'm going to have to erase these points in a second. Some of you might just try to visualize them. If I start here and I go up 1 over 1, I would go here, 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 here. Oh man, I didn't make my graph big enough. So in terms of what I'm going to graph, I'm only going to graph out of this whole line everything from here over. Then I have to somehow get rid of these blue dots. So it's 3 pieces. It's this piece, and then it changes and it goes on forever. And this part is a curve.
So that's what that whole section is, just graphs.
Mm-hmm. It's a lot of graphing.
Why do you do this? It's the end of the year, it's just easy.
I just had you graph I had you graph lines. Piecewise functions.
That's not a line.
Whatever this is. That's all. That's what this is piecewise functions. This will be something you will probably do this stuff. I'm thinking right now I'm leaning towards a shorter quiz instead of putting this stuff onto the exam, I'm leaning towards we'll quiz on it at the end of next week before our exam, because I already had your exam written without this chapter. So that's what I'm thinking of leaning towards, is just, we will quiz over it though, and you are responsible for showing me you can do these pieces. Do you want to try one and see if you can, and see where you get stuck?
Why not?
Why not? Here, take this one. It's done in 3 pieces. At least one of them's a line, one of them's a parabola. So we've already talked about those and remembering how to graph them. The third one's a cubic, the one in the middle. So I want you to try thinking about the stopping points on this one. It's got 2 of them, 0 and 1. There's going to be some tiny pieces smushed in the middle. I want you to see if you can graph it. So looking around, your first piece is the easy piece. The middle piece is such a tiny piece. And you want to try to get the shape in there as best you can. So what I do is I think about the left and right side. So I go 0 cubed and 1 cubed. That means that this one's going to be here, and it's going to be here. And then as far as what goes on in between, anyone know? Yeah, it is, because overall the x cubed graph looks like this. And so you just see this tiny little piece of a curve, basically. It almost looks a lot like the x squared at that point. So then I could think about the last one, and that's where it's just a line, but the hard part is you don't graph the part on the y-intercept, but you can graph it in your head or graph it lightly and then erase it. That might make it easier, so I'd go like that. Yeah, up to over 1, which means it goes here, here, but I'm going to start here, so I'm going to go like that. Whoops, I got kind of out of control. There he is. Good. So they're not scary. They just take some time, and it's kind of cumbersome because you're doing multiple problems within a problem.
On like the quiz, will it be okay to use our calculator to graph it to see what it look like? Or?
You can graph them like that. Now, ultimately, in the long run, I'd want you, the more of these we see, so as you see more and more of them, I'd want you to get the pictures in your head too, because that's going to be a lot faster than trying to graph them on your calculator and get the pieces. The calculator actually can't graph these. You can do the restrictions. Some of you did them last year. Was it just last year that we had that? When you did that project where we did the conics? Do you remember? I know, yeah, I remember Trent doing it. Some people looked up, when I told you could look up how to actually do the restrictions and tell it to only graph a piece of piece, but it is kind of cumbersome, like in terms of all the stuff you have to type in. You didn't think so? Not bad. I don't know. I don't like typing them in and telling the calculator the restrictions because it's kind of, I don't know, takes a lot of time. So if you can kind of chop them into pieces in your head, that would be best. Questions? Okay. Last thing I want us to try then together is we're going to try 2, where we're going to actually write a piecewise function. So I want you to look up here, and your goal is to figure out what the 2 pieces are. So you're going to try to break it into as many chunks as you need to in terms of where the graph changes, and you have to know where it changes. So when you look at 41 up here, how many pieces do you see that look different? 2. Okay. You see 2. Where do they start and stop?
First one starts at 0 and stops, and the second one starts at 0.
Okay. So in terms of me figuring out what this piecewise function looks like, there are 2. So every piecewise function starts out as f of x equals or y equals, and then you've got a space to show your pieces. The bracket's supposed to tell you this is all one function. So I have to know what this first left piece looks like. So I'm only caring about this for now. It's a line. That's good. It's x. Why is it x? What, every line just going to be an X?
No, it's like 1/1.
Okay, F1/1, and it had a y-intercept of 0. So it's just X. And then you're going to define for me, where do you want me to graph it? So you have to pay attention to open and closed circles and arrows.
0 and 1.
This one is between 0 and 1. Does it include 0 and 1?
Yes.
So I would graph a restriction that looks like that. So that's the first piece. Then I look at the next piece. You'd say it's a line. So I need some sort of function. That's where it gets a little tricky, because you have to know the slope and you have to know the y-intercept.
So would be negative x plus 2.
Good. Negative x, I can count down 1/1. How did you get to the plus 2, Riley?
Because the slope is 1/1. That's like 1 and that's 1.
So you just basically traced it in your head, you're saying, and figured out the point, so you followed your slope. Perfect. And then you tell me to graph this between...
1.
Okay. Now here's the hard part. In terms of your symbols, generally when we're reading piecewise functions, each x value can only be accounted for once. So it does include the 2, but in terms of which piece includes the 1, they don't really specify, because you can see right here that it is definitely dark. But what you want to do in terms of your function then is choose 1. So the fact that I've already said including 1 on the top one, I would leave this as less than. It's not going to make a difference in terms of if I gave you an x value to plug in, because if I tell you to plug in 1, which is what we'll end up doing with these later, you'd read and you'd say I need to plug it into this one, and I'd get 1. I'd get 1 here too. But you just want to be careful that when you're defining your pieces, you're only accounting for each x value one time. So I'm going to leave this one open, even though technically it doesn't make a difference in terms of the x value. So then on 42, how many pieces do you see? So you could define this as 4 separate pieces. 2 of them go together and 2 of them go together. So you could really say it's 2 pieces, but you'd have to give multiple restrictions. Most people would probably give this one 4 different pieces and give it just those couple of restrictions. So look at the first piece. What would you call that? Okay. And where do you want me to graph it?
0 and 1.
Okay.
Equal.
Does it include either of those points?
0.
It includes 0, but it does not include the 1 because it's an open circle. And then the next piece is
0.
Yeah, 0. Yeah, between 1 and 2. And which one do I include?
1 and 1.
Yep, so I'm going to put an or equal to under that.
So can't you just do the same thing? Like, can't you just do the 2 restrictions for the 1, 2, and 2 restrictions for the 1?
So give it 2 restrictions, you're saying? Yes. That's what I was saying earlier. Because they are actually the same line, I could also put like this and another restriction, or because I'm kind of out of space, I could also define them as 4 pieces. What's that?
Those dotted lines actually lines or no?
No. So then I would go here and I could say, so I'm going to do this one between 2 and 3.
Would be less than or equal to.
Yep, that one should be a less than or equal to.
It should be 3 less than or equal to x. Less than.
Perfect. And I would stop there. Oh, less than or equal to 4, because it actually does close there. You think you got it? Got the basic gist? Okay.